Good afternoon. I welcome you all to this lecture session of the course Laws of Thermodynamics. Last class we have seen that the change of entropy delta S in an adiabatic process is greater than 0 always because of internal irreversibility, even if there is no heat transfer. If the process is reversible, that internal irreversibility is 0, then a reversible adiabatic process, no question of external irreversibility because the process is adiabatic, equals to 0. These two important things we have come to know at the conclusion of the definition of the entropy through Clausius inequality. Now, an isolated system which does not interact with the surrounding may be considered as an adiabatic system. There may be changes that can take place within the system. System may not be at equilibrium state. And these changes, if it is irreversible, we consider, then delta S we can consider as isolated system is greater than 0. If we consider the changes inside the isolated system that takes place from one part of the system to other part, if you consider a single system, delta S isolated in case of reversible changes, reversible changes equals to 0. So, these two combined, we can write delta S of an isolated system is greater than equals to 0, means that the change of entropy of an isolated system is greater than 0 if the changes within this system is irreversible, or if the changes within this system is reversible, then equality sign holds good. Now, in this context, is very important thing is that if we have two systems, system A and system B interact with each other in terms of energy, mass, everything. These two systems as a whole, and if they do not interact with anything else in the surrounding, the two systems itself constitute an isolated system. And this is not for two systems. If we have number of systems A, B, C, they are mutually interacting with each other, can make an isolated system. And this type of isolated system in a very loose term is known as universe. That means we consider in our universe there are processes takes place between system to system, we interact with each other, there is number of interactions takes place, but universe is such that it does not interact outside the universe. So, entire thing is within the universe. So, with that limited sense, in classical thermodynamics, an isolated system which constitutes interacting systems in the surrounding as universe, and therefore, and they behave like an isolated system. Obviously, I told that constituting these interacting systems, and therefore, we can write with this that delta S universe is greater than equals to 0. That means, if we consider an isolated system consisting of interacting systems, either two or more number, then delta S of this combined system is greater than 0 when the interactions will be, when the interactions will be irreversible, when the interactions will be reversible, delta S universe will be equals to 0. And delta S universe, that means of this isolated system, is nothing but sum of delta S of all the interacting system A plus delta S B plus delta S C, all the interacting system. Algebraic sum of all the, that means some may be positive, some may be negative, in such a way that their algebraic sum is always either 0 for a reversible process or greater than 0. For any natural process, for example, two bodies exchange heat. I will show you now, if the two bodies exchange heat, one body which rejects heat, his entropy is decreased, but one body which gets heat, entropy is increased. But the algebraic sum is greater than 0 if the process is an irreversible or natural process, otherwise it is 0. if it is a reversible process. If there are two systems, one is considered as system, another is considered as surrounding to that system, sometimes we write this expression also, delta S universe is equal to delta S system plus delta S surrounding. That also can be written, delta S universe, delta for two system, one is system, another is surrounding. Now you see this concept, how does it work? Now let us consider an irreversible heat transfer process. Let us now consider an irreversible heat transfer process. An irreversible heat transfer process. T1, an irreversible or natural heat transfer process will take place if two systems are made into contact through a diathermic wall, so that heat can transfer. In this case where T1 is greater than T2, heat will come. So now entropy change of this system, this is system A, this is system B. Del S A is minus Q by T1. Why? Delta Q by T is Q by T1. Okay? And this is del S B is Q by T2. And if we consider the changes internally are reversible, so that we can write that delta Q by T is del S A. And since T remains constant at T1, T1 comes out of the integral, this becomes Q. And the same Q is transferred here, Q2. So delta S universe will be equal to Q into 1. This is minus 1 by T1 plus 1 by T2. So this is always greater than this because T2 is less than T1. T1 is greater than T2. That means this is less, that means this is always greater than 0. Another example I give, if the two bodies are of finite capacity, here you have considered thermal reservoir whose heat capacity is infinitely high and keeps at constant temperature. But if I make contact of two finite bodies T1 and T2 and heat transfer takes place, so that T1 gets decreased, temperature gets decreased as it rejects heat, and T2 gets increased as it takes heat. And the heat transfer will go on decreasing as the temperature difference goes on decreasing, and finally the process will naturally stop when that will attain a mean temperature. If we consider the heat capacities are same, then you know the mean temperature is nothing but the arithmetic mean by the energy balance T1 plus T2 by 2. That means heat rejected by this body is equal to the heat gained by this body. And if we consider Tf is the final temperature, as you know that if the heat capacities are same, Tf is the arithmetic mean. But now instead of, though this is a natural process, this is a Tf is T1 plus T2 by 2. Now how do you find out the delta S universe? So delta S universe equals to delta S, this is body A, let this is body B, delta S A plus delta S B. Now what is delta S A in this case? Delta S A, if we consider this is internally reversible, is integral del Q by T for the body, and heat is equal to Cp is the heat capacity, total heat capacity, mass into specific heat, Cp into dt is the reversible heat transfer divided by T, and it is from T1 to Tf, and this becomes is equal to Cp ln Tf by T1. Since Tf is less than T1, this is negative. Obviously, the delta Sa is negative because for A it is rejecting heat, it is cooled. So therefore, we cannot take T out because delta Q is Cp dt and T is changing. So therefore, you have to integrate like this. Similar way, delta Sb comes about to delta Q by T. This is for A, this is for B, and that becomes is equal to just the similar way Cp ln Tf by T2. And this is positive because Tf is greater than T2. So delta S universe is equal to delta SA plus delta SB Cp ln Tf square divided by T1 T2. And Tf square is what? Cp ln T1 plus T2 whole square, T1 plus T2 by 2 whole square divided by T1 T2. This is always positive, we can prove. This is because we know that geometric mean root over T1 T2 is always greater than the arithmetic mean. This we have proved, that this we can prove that T1 plus T2 whole square is always greater than T1 T2. That means it is always greater than 0. That means it is greater than 0. So we can prove, since the arithmetic mean is greater than the geometric mean, that is T1 plus T2 by 2 is always greater than T1 T2 root over T1 T2, or this whole square is greater than T1 T2. We can prove, simple school level algebra, so that entropy change is greater than 0 for a finite body. Now another very interesting thing comes into picture, that if the two finite bodies are attached or connected through a reversible heat engine, then what will be its final temperature? This is a very interesting problem. That if two bodies A at temperature T1, another body B at temperature T2, if they are connected through a reversible heat engine, sometimes this is a problem that it takes heat Q1 which is going on changing because they are finite capacity bodies. So what will be Tf and what will be delta S universe? Tf is not the arithmetic mean, so you have to find out Tf because they are not in direct thermal contact. Now here, to find out Tf, we must know this thing. This will act as a clue to find out Tf. Since this is the internal irreversibility is taken to be 0 for both these things, and since this is connected to a reversible heat engine which takes also heat reversibly from these two reservoirs, so the entire process is reversible. This system reversible, heat engine reversible, this. That means delta S universe is delta S A plus delta S heat engine plus delta S B. Now for a heat engine, whether it is reversible or irreversible, the entropy change is always 0 because entropy is a property and it operates on a thermodynamic cycle, 0. And delta S A and delta S B, they are all operates on a reversible process, so that delta S A and delta S B summation, algebraic summation will become 0. So delta S universe will be 0. That means delta S A plus delta S B is equal to 0. We take this clue to find out Tf. What is delta S A? That means delta S universe is equal to delta S A. It will be the same equation, ln Tf by T1 integral delta Q by T plus Cp ln Tf by T2, so that this is Cp ln. This expression will remain same earlier one because this comes from the integral dq by T, del Q by T, and in this case this becomes equal to 0. That means Tf square by T1 T2 is 1, ln Tf square T1 T2 0. That means Tf is geometric mean. So in case of direct thermal contact of two finite bodies of same capacity is arithmetic mean, while it is connected by a reversible heat engine, internal irreversibilities of the systems are 0, then the mean temperature is root over T1 T2 is the geometric mean. Okay. Now after this I will solve few problems. Okay, I think the concept is clear to you. Therefore, you see, before I close this, I tell you that it is now concluded that for all natural processes in this universe, which is considered as an isolated system, takes place in such a way that the delta S of the universe is greater than 0. And this is the directional constant I told at the beginning of this class, that there is a directional constant for any process. Any natural process occurs in such a way that it makes a permanent indentation to the surrounding. That means the entropy change of the process plus the entropy change of the interacting systems or surrounding, algebraic sum of these two must be greater than 0 if the processes are natural. That means if you consider an entropy bank in an universe, the entropy is monotonically increasing. That means entropy change of the universe always increases. For example, I am teaching to you, this is a process. In this process, I increase the entropy of the universe. So there is an increase in the entropy of the universe. Entropy is generated in the universe. So this is the directional constant of any natural process, okay, in general. Now I will solve some problems. Let us see this problem. A heat pump has a coefficient of performance that is 50% of the theoretical maximum. A heat pump has a coefficient of performance that is 50% of the theoretical maximum. It maintains a house at 20 degrees Celsius which leaks energy of 0.6 kilowatt per degree of temperature difference to the ambient. That means temperature difference from the house and the ambient. For a maximum of 1.0 kilowatt power input to the heat pump, find the minimum outside temperature for which the heat pump is a sufficient heat source. Okay. Now let us come to the board and see what this tells. Now there is a house. This is the house, and there is a heat pump. Let the temperature of the house is TH, which is 20 degrees Celsius, means 293 K. Actually it is 273.15, you have to add, because the thermodynamic scale of temperature is defined, which has been defined as I told, but the scale is like that. 0 degrees Celsius corresponds to 273.15 Kelvin, but you can neglect this 0.15, 293 K. And heat pump gives heat QH to this house, and it takes heat from the surroundings. This is the surrounding temperature TA, which we have to find out. So this takes heat from the surrounding. Let this is QA. We have to find out TA, and it takes work as 1 kilowatt. Let us work with the 1 kilowatt heat and find out what is the value of TH, and that will be TA, and that will be the minimum value. Why, I will tell you afterwards. This house leaks energy which is QL, is the heat at which the heat leaks from the house to the surrounding. Now to maintain the house at 293 K, ambient will be automatically, by common sense, is much less than 293 K. It is the heating the house in winter in western countries. Now this QH will be such to maintain the house at 293 K must equal QL. That means the heat which it leaks must be given by QH at steady state when the house has attained 293 K. That means QH will be equal to Q leak, and Q leak is, it is what, 0.6 kilowatt. What is this? The Q leak is 0.6 kilowatt per degree of temperature difference. That means 0.6 into TH minus TA, that much kilowatt. TH minus TA, because by definition 0.6 kilowatt per degree difference, TH minus TA, QL, this is QH. Now we have to express QH now in terms of this temperature TA and TH, so that we can find out the TA, minimum temperature T. How you will find out? Now this QH can be written as the coefficient of performance of the heat pump into W, because coefficient of performance is defined as QH by W, and W is equal to 1. So therefore it is simply the COP of the heat pump, that much kilowatt. Why? Because W is 1 kilowatt. Now we have to express COP in terms of the temperatures, and it is written in the problem. The heat pump has a coefficient of performance which is 50% of the ideal one. That means COP of heat pump is 0.5 of the COP of the ideal. Now ideal COP we can write, COP is usually can be written W by QH or extremely QH by W or QH by QH minus QA. And for a ideal COP, this is the basic definition. They are proportional to their temperature. So therefore COP will be 0.5 of this. So therefore we can write QH is equal to 0.5 of this. That means QH is equal to QH is equal to COP of heat pump, W is 1. So QH is equal to 0.5 TH by TH minus TA. Very simple problem. TA, small a, I have given small a, sorry, TA, TH minus TA, and that must be equal to 0.6 TH minus TA. Okay, so therefore it must be equal to 0.5 TH minus TA must be equal to 0.6 TH minus TA, because this is QH is equal to QL. So therefore we get TH minus TA whole square is equal to TH minus TA whole square is equal to 0.5 by 0.6 into TH. This is very simple. 0.5 by 0.6, 0.5 by 0.6 TH is TH minus TA, and if you solve it, TH is 293 K, you get the value of TA. The negative value you just ignore, which will give a value of TA higher than TH. So we take the positive value, the answer is 277.4 K, 277.4 K. That means TA is in the usual centigrade or Celsius scale is 4 degrees Celsius. So this is simply this problem. Okay, I think you have understood this problem well. So how I have done that, QH is equal to QL at steady state, and QL is by definition this. QH is COP into W by definition of COP heat pump. W is 1 kilowatt, so therefore simply it is COP HP kilowatt. So then we write COP of the heat pump is 0.50% of this. This is ideal. We cannot write in terms of temperature for a non-ideal heat pump, but it is 0.5 of the ideal heat pump COP. So therefore QH is equal to COP is equal to this is equal to 0.6 TH minus T. Okay. Now we come to the next problem. Now we come to the next problem. Now this is the same problem. We wish to produce refrigeration at minus 30 degrees Celsius. A reservoir is available at 200 degrees Celsius and the ambient temperature is 30 degrees Celsius. A reservoir is at 200 degrees Celsius and the ambient temperature is 30 degrees Celsius. Thus work can be done by a cyclic heat engine operating between 200 degrees Celsius reservoir and the ambient. This work is used to drive the refrigerator. Determine the ratio of the heat transfer from 200 degrees Celsius reservoir to the heat transfer from minus 30 degrees Celsius reservoir, assuming all processes are reversible. Now this is like this. We have ambient, we have a hot source at 200 degrees Celsius. that means 473 K. This is TH, hot source. Then we operate a heat engine with the ambient. The heat engine takes heat Q1 and rejects it Q2 to an ambient temperature TA, which is how much? TA is an ambient 30 degrees Celsius, TA, which is equals to 30 degree, that means 303 K. 30 plus 273, 303 K. Now this heat engine drives a heat pump or a refrigerator. Here you write refrigerator. Refrigerator which takes same thing, heat pump, the same device is heat pump or a refrigerator, takes heat from minus a cold temperature TL, low temperature, which equals to minus 30 degree Celsius. That means this is what is that? Minus 30 degrees Celsius. Okay, let me see. The minus 30 degrees Celsius. That means it is 243 K. It takes QL and it gives to the ambient temperature. Ambient temperature, in case here is the sink, it pumps heat from the low temperature and gives to the ambient temperature, which is 303 K. And this heat you consider as QH, which it gives here. So Q1, Q2 are the heat taken in by the heat engine, given by heat engine. This is by the refrigerator, given by the refrigerator to this, where it acts as a heat pump. Now our problem is that we have to find out Q1 by QL. What is Q1 by QL? So it is very simple that W is the connecting thing. That means we connect W with Q1 and then we connect W with QL and equate it and we get the result. Because the same W is driving the refrigeration. We have a temperature this from where refrigeration has to be made. And we have an ambient where the refrigerator will reject heat. But we have a source, so that with this as a source and the ambient as a sink, a heat engine can operate and that heat engine can drive the refrigerator. That means same W. So from the heat engine, we get what? We get W is Q1 into eta. And here all processes are reversible. It is told in the problem that assume all processes are reversible. So eta is what? Q1 into 1 minus eta is TA by TH. TA by TH. 1 minus TA by TH. So W1 is Q1 into 1 minus TA by TH. From here W, how can I find out? W here, COP is defined as from refrigerator. From refrigerator, COP is what? COP is QL divided by W. That means QL divided by W. So QL is equal to, therefore W is equal to QL by COP. Okay. And at the same time, COP, since this is a reversible heat pump, COP is QL divided by QH minus QL, that is TL divided by TA minus TL, because it is a reversible heat pump or refrigerator, so you can express this in terms of their temperatures. TL divided by TA minus TL. TL divided by TA minus TL. Okay. So now W is equal to what? From the refrigeration, from the refrigerator, we get W is equal to QL by what? W is equal to QL by COP, and COP is that, so W is equal to QL into 1 by COP. That means TA minus TH, TA minus TH divided by TA minus TL, sorry, Ta minus TL divided by TL, that is this temperature. So, these two are equal W. So, therefore, Q1 into 1 minus Ta by Th, that is the efficiency, QL into Ta minus TL divided by TL. Now, here we get everything. So, we get Q1 by QL. Q1 by QL, if you take this side divided by this, we know Ta 303, we know Th 473, and we know TL is 243. So, you know all the temperatures. So, therefore, we can get the ratio Q1 by QL, which is equal to 0.687. 0.687. Okay. So, today up to this. Thank you.